Hey there, welcome back finally to another episode of Graph Theory with Python. My name's David Amos, and I'm coming to you from my new office space, which has yet to be decorated. I've still got to do a little bit of acoustic treatment on the walls and things like that to get a little bit better sound quality, but it's getting there, and I'm absolutely loving having this new space. This video is part 4 of Graph Theory with Python, and we're going to talk about the degree of a vertex. We'll talk about what that means, how we define it mathematically, and how we can compute it using Python. We'll also explore some of the properties of degree and investigate something called the Handshaking Lemma, which is going to take us all the way back to Leonhard Euler, who we talked about in part 1. Finally, we're going to talk about something called the degree sequence of a graph. There's so much to say on this topic that this is actually going to be a 2-part video. In the next part, which is part 5 of Graph Theory with Python, we'll explore degree sequences in a lot more depth. So let's get to it and talk about this thing called degree.
To understand degree and where it comes from, let's go back to the 7 Bridges of Cologne, which we talked about in part 1 of the Graph Theory with Python series. If you watched that video, and if you haven't, I highly recommend that you do, then you'll recall that the city of Königsberg has 4 landmasses separated by a river that forks. Here's Leonhard Euler's diagram that he drew in his paper about the Bridges of Königsberg. He labels the 4 landmasses A, B, C, and D. The 4 landmasses are connected by 7 bridges, labeled with lowercase letters in Euler's diagram. There's bridge A, bridge B, bridge C, bridge D, bridge E, bridge F, and bridge G. One of the things that mathematicians do is look for patterns. Euler did it, and so did mathematicians before him. During his investigation to the 7 Bridges of Königsberg problem, he may have made a table that looks something like this. This table looks at the number of bridges connected to each landmass. For example, there are 5 bridges connected to landmass A. Bridges A, B, C, D, and E. There are 3 bridges connected to landmass B. Bridges A, B, and F. There are 3 bridges connected to landmass C. Bridges C, D, and G. And there are 3 bridges connected to landmass D. Bridges E, F, and G. Let's write down the number of bridges connected to each landmass. Landmass A has 5, and landmasses B, C, and D all have 3 bridges connected to them. Euler noticed something about the sum of the number of bridges connected to each landmass. If we tally them up, we have 5 on landmass A, plus 3 for B, which gives 8, plus another 3 for C, we're at 11, plus another 3 for D, giving us a total of 14. This happens to be twice the number of bridges, since there are 7 bridges. And this isn't an accident. Euler gave a pretty clear explanation of why. If you look at the list of bridges in the table associated with each landmass, you'll notice that each bridge appears exactly twice. For example, bridge A appears in the row for landmass A and landmass B. Bridge B also appears in the row for landmass A and landmass B. Bridge C appears in the row for landmass A and landmass C, and so on. Each bridge appears in the table twice because it's connected to exactly 2 landmasses. So when we add up all of these numbers, we're really counting each bridge twice. So for any configuration of landmasses and bridges, if you make a table like this and count the number of bridges connected to each landmass, then add all those numbers up, you'll always get twice the number of bridges. And since twice of any whole number is even, that means you'll always get an even number. So what does degree have to do with this? Well, the number of bridges connected to each landmass is the degree. So 5 is the degree of landmass A. What we've done is given something a name. The number of bridges connected to a landmass is called the degree of the landmass. And it allows us to write the statement, the sum of the number of bridges connected to each landmass is always an even number a little bit more compactly. So we can say the sum of the degrees of each landmass is even. And we've now got a theorem about all configurations of bridges and landmasses. I mean, that's pretty cool, but how do we turn this into something about graphs? Euler never drew a graph. He never even talked about graphs. Everything he talked about was through the frame of landmasses and bridges. But we can convert Euler's diagram of Königsberg to a modern graph representation. We draw a node, or a dot, for each landmass, and an edge between two nodes if there's a bridge that connects the corresponding landmasses. If I remove Euler's diagram, I'm left with the picture of a graph. Now this picture represents the exact same configuration of landmasses and bridges, just in a more abstract way. Each node is a landmass, and each edge is a bridge. So if the degree of a landmass was the number of bridges connected to it, then we can come up with a rough definition of degree in a graph. The degree of a node is the number of edges connected to it. In more mathematical jargon, you might hear the word connected replaced with incident. So let's make a quick table of each node and its degree for this graph. But first, we need to label each node. I'll use the numbers 0, 1, 2, and 3. Node 0 has 5 edges connected to it, so it has degree 5. Node 1 has 3 edges connected to it, so it has degree 3. Node 2 also has 3 edges connected to it, so it has degree 3. Finally, node 3 also has 3 edges connected to it. So just like nodes 1 and 2, it has degree 3. Now earlier, I called this definition a rough definition of degree. That's because it's not super precise. For example, let's say I add a loop to node 3. A loop is an edge that starts and ends at the same node, like this. What would you say the degree of node 3 is now? Well, I only added one edge, so shouldn't the degree be 4? Not exactly. Now, this might seem kind of weird, and honestly it is, but if you have a loop on a node, it contributes 2 to the total degree of the node. So with the loop, node 3 actually has degree 5. Why is that? Well, remember how Euler discovered that the sum of the number of bridges connected to each landmass is always an even number. If we have loops in our graph, and we say they only add 1 to the degree, then that statement's no longer true. You can see that for yourself here. If we say that node 3 has degree 4, then the total sum of the degrees of all the nodes ends up being 15, which is not an even number. In order to maintain this balance and always get an even number, we just define loops to contribute 2 to the total degree of a node. I mean, why not? But loops are kind of weird, and a lot of times we're just going to exclude graphs with loops from our discussion. Not all the time, but most of the time. So let's get rid of this loop. Now let's talk about 2 special degrees, the minimum and maximum degree. The minimum degree is the smallest degree among all degrees of all nodes in the graph. Mathematicians love Greek letters, and the minimum degree is usually denoted with a lowercase Greek delta. In this graph here, there are 4 nodes with degree 1 and 2 nodes with degree 3. Since 1 is smaller than 3, the minimum degree for this graph is 1. The maximum degree is the largest degree among all nodes in a graph, Mathematicians denote the maximum degree with a capital Greek letter delta. In this graph, the maximum degree is 3. Up until now, we've been talking about degree in undirected graphs. Now let's talk about how it works in directed graphs. That is, graphs where the edges have a direction, which we indicate with an arrow. Let's take a look at an example. Here's an example of a directed graph. The edges are arrows, and they point from one node to another. They have a starting node and an ending node, something that doesn't happen in undirected graphs. So from the viewpoint of a node, an edge can either be pointing towards the node or pointing away from it, coming into the node or going out of the node. For this reason, it makes sense to talk about two different kinds of degrees. The in degree of a node is the number of edges pointing into a node. For example, this node right here has one edge pointing into it. So the in degree of that node is 1. The in degree doesn't always have to be positive though, even if there's an edge connected to the node. For example, this node has no edges pointing into it, so it has in degree 0, even though there's one edge pointing away from it. The out degree of a node is the number of edges pointing away from a node. For example, this node has 2 edges pointing away from it, so it has out degree 2. Just like in degree, out degree can be 0. Can you find a node on this graph that has out degree 0? There's just one. This one right here. There's actually one more type of degree you can talk about in directed graphs. The total degree of a node is the total number of edges connected to that node. For example, this node has one edge pointing into it and 2 edges pointing away from it, so it has total degree 3. So there are 3 ways to think about degree in a directed graph. If you take the direction of the edges into account, you can talk about in degree and out degree. If you ignore the direction of the edges, you can talk about the total degree. Since there are 3 ways to look at degree in directed graphs, there are 6 ways to define minimum and maximum degree. You can talk about minimum in degree, which is the smallest in degree among all in degrees in the graph, and maximum in degree, which is the largest in degree among all in degrees in the graph. Remember how mathematicians love Greek letters? Well, they use them here too. And just like in undirected graphs, they use the lowercase and uppercase Greek letter delta for minimum and maximum degree. But for directed graphs, we also have to take into account the type of degree we're talking about, in degree or out degree. In a lot of mathematical texts, you'll see a minus sign used as a subscript to indicate that we're talking about in degree. Why the minus sign? Well, I'm sure there's a reason, but I don't like it. Instead, I'll just write the word in as subscript to indicate that we're talking about in degree. Can you find the minimum and maximum in degrees in this graph? The minimum in degree is 1, and there are 2 nodes that have minimum in degree. This one and this one.
Hi, it's David from the future when I'm editing this video. And no, the minimum in degree is not 1. It's 0. There's one node with in degree 0. It's the one on the far left. So, yeah.
And maximum in degree is 2. There's just one node with the maximum in degree. This one right here. In addition to minimum and maximum in degree, you can talk about minimum and maximum out degree. Again, mathematicians use the lowercase and uppercase Greek letter delta. In a lot of mathematical texts, you'll see a plus sign used as subscript to indicate that we're talking about out degree. As you might guess, I'm not a big fan of that. Let's just use the word out. Take a moment to find the minimum and maximum out degrees in this graph. The minimum out degree is 0, and there's one node with that out degree. This one right here. The maximum out degree is 2, and there's one node with that out degree, the one right here in the middle. Finally, we can talk about the minimum and maximum total degree. Just like before, we'll use the lowercase and uppercase Greek letter delta, and we'll write the word total in subscript to indicate that we're talking about the total degree. So now, pause for a second and see if you can find the minimum and maximum total degree in the graph. The minimum total degree is 1, and there's one node with that degree, right here. The maximum total degree is 3, and there's one node with that degree, the middle one. Now we haven't talked about loops in directed graphs, so let's address that for a second. Let's say I have a loop on this vertex here. For undirected graphs, we said that a loop contributes 2 to the degree of a node. Well, it's kind of the same for directed graphs, but only when talking about total degree. For in degree, it just adds 1, because we've just added one more edge coming into that node. The same goes for out degree. We've added one more edge coming out of that node. So the in degree and the out degree have both increased by 1, but the total degree has increased by 2. That's another good reason for why loops add 2 to the degree of a vertex in an undirected graph. We get this nice symmetry with the concept of total degree in a directed graph. And since total degree ignores the direction of the edges in a directed graph, it's kind of like looking at a directed graph as an undirected graph. If you look at a single node in a directed graph, say this one, then the total degree is 3, which is the same as the sum of the in degree and out degree. That's true for any node. In degree plus out degree is equal to total degree. But what about minimum and maximum in and out degrees? If you add those together, do you get the minimum or maximum total degree? To write this using the notation we've introduced, does the minimum in degree plus the minimum out degree equal the minimum total degree? And does the maximum in degree plus the maximum out degree equal the maximum total degree? Let me know what you think in the comment section below. And in a few days, I'll post another video going over the solution.
Okay, so now we know what the degree of a vertex is, and we know how to compute it by looking at the picture of a graph. But how do we compute it using Python? Let's jump into a code editor and check that out.
Here's the graph.py file that we've been building up throughout this Graph Theory with Python video series. We define a graph as a name tuple that contains a list of nodes, a list of edges, and a Boolean flag that tells us whether or not the graph is directed. We define 2 ways to represent a graph in computer memory. The adjacency list, which we call the adjacency dict, because it uses the Python dictionary data structure to represent the adjacency list, and the adjacency matrix, which uses a 2-dimensional Python list to represent the adjacency matrix of the graph. In part 3 of this series, we defined some convenience functions that we could use to generate special graphs. We have a path graph function for generating paths, a cycle graph function for generating cycles, a complete graph function for generating complete graphs, and a star graph function for generating star graphs. If you aren't sure what those are, then I recommend you go back and watch part 3 of Graph Theory with Python. It explains what those graphs are and how we wrote the code for these convenience functions. Now I'm going to open a terminal and execute graph.py. I'm using the -i flag when running Python to run this module interactively. So it'll execute graph.py, then drop me into a Python shell where I can interact with everything we've defined. Let's start by creating a star graph on 5 vertices. And here's what that graph looks like. It has one node of degree 4 in the center, and 4 nodes of degree 1 connected to the degree 4 node. So we want to be able to compute the degrees of each of the nodes in our star graph. Remember, G is just a named tuple. We could get the list of edges by accessing the edges attribute. We could iterate over this list to try and determine how many times each node appears in an edge, but we'd have to loop over that list many times, and that's not very efficient. Let's take a look at the adjacency list representation. The dictionary representing the adjacency list has keys that are the nodes in the graph, 0, 1, 2, 3, and 4, and values that are lists containing the nodes that are adjacent to the key. Well, if a node is adjacent to another node, that means there's an edge between those two nodes. So there's an edge connecting those two nodes. Do you see where I'm going here? The degree of each node is just the length of the list in this dictionary. So to get the degree of node 0, I just call the len function on this list. Let's give the adjacency list a name. I'll call it adj_list. Then I'll call the len function on the value returned by key 0. And there we go. We have the degree of node 0. I can do this for any node in the graph. If I wanted to get the degree of node 4, I'd just replace this 0 with a 4. This is one of the things that makes the adjacency list representation so useful. It not only captures the structure of the graph, but allows us to efficiently compute various properties of the graph. Now let's look at the adjacency matrix of our graph. That's a little hard to read. It doesn't really look like a matrix like this. So I'm going to use the pprint function from the pprint module to pretty print this two-dimensional list. Pardon this little hanging parenthesis. Sometimes it's a little hard in the standard Python shell to see whether or not you've matched all of your parentheses. Okay, so this gives us a better look at the adjacency matrix. If you remember from part 2 of graph theory with Python, the adjacency matrix has one row for each node in the graph. This row corresponds to node 0, this row corresponds to node 1, and so on and so forth. Similarly, the columns correspond to each node. So this column corresponds to node 0, this column corresponds to node 1, and so on. We put a 0 at a position in the matrix if there's no edge between the row node and the column node. Since there's no edge between node 0 and itself, i.e. there's no loops in this graph, we put a 0 there. We put a 1 in a position in the matrix if there is an edge between the row node and the column node. Since node 0 is adjacent to node 1, we put a 1 in this position. So each row has a 1 in it if the row node is adjacent to that column node, and a 0 if not. So we can also use the adjacency matrix to compute the degree of a node. All we need to do is just count the number of 1s in each row. Or even better, we could just add up all the values in this row. To do that, we'd use the sum function. Let me give the adjacency matrix a name. I'll call it adj_matrix. To get the row corresponding to node 0 in the adjacency matrix, I use the subscript notation with the value 0, like this. So to get the degree of node 0, I just need to pass that to the sum function. And just like that, I've got the degree of node 0. If I wanted to get the degree of node 4, I'd replace this 0 with a 4. So just like the adjacency list representation, the adjacency matrix representation also makes it easy to compute various properties of a graph. The downside to the adjacency matrix is it usually requires more memory. It's a larger data structure. So let's quit the Python shell and head back to our graph.py file and write a function that returns the degrees of nodes in a graph. Here's a function called degrees. It has one parameter, expected to be a graph, and it returns a dictionary of degrees for each node in the graph. So if we go back to the example of the star graph on 5 nodes, this function should return a dictionary whose keys are the nodes 0, 1, 2, 3, and 4, and whose values are the degrees of each of those nodes. We're going to use the adjacency list representation of the graph in order to compute the degrees, because in general, adjacency lists use less memory than the adjacency matrix. I've chosen to use a dictionary comprehension. This converts the adjacency list dictionary into the dictionary of degrees that I want. Each key of the dictionary is the node, which is just the key in the adjacency list dictionary, so the keys stay the same here. The values, though, take the list of neighbors, a neighbor being a node adjacent to some other node, and passes that list to the length function to calculate the length of that list. It does this for each pair of node and list of neighbors in the items of the adjacency list dictionary. Finally, it returns that dictionary. Let's see this function in action. I'll run the graph.py file interactively again. Then I'll create our star graph on 5 nodes and assign it to the name g. Now let's call the degrees function on g. Look at that. We've got a dictionary whose keys are the nodes in the graph, 0, 1, 2, 3, and 4, and whose values are the degrees of those nodes. Node 0 has degree 4, and nodes 1, 2, 3, and 4 all have degree 1. If I want to get the degree of a specific node, then I could assign the dictionary returned by degrees of g to some variable, let's call it degrees underscore g, and then I use the dictionary subscript notation to access the value for whichever node I want. Let's get the degree of node 0. There's an assumption we made about the graph in the degrees function, though. Can you guess what it is? We implicitly assumed that the graph passed to degrees is an undirected graph. What do you think would happen if we passed a directed graph to the degrees function? Do you think it would return something useful? Let's find out. Let's take a look at our star graph. We can create a directed version of this pretty quickly by copying the output, changing is directed to true, and assigning it to a new variable name. Let's call it g_dir for directed. So before we pass this to the degrees function, let's think about what we should get here. We still have 4 edges, but now these are directed edges. So the edge between 0 and 1 starts at 0 and points towards 1. The same with the edge between 0 and 2. It starts at 0 and points towards 2. Same for this one and this one. All the edges start at node 0 and point away from it. Well, I accidentally used graph G here, but it's the same list of edges as g_dir. Let's pass g_dir to the degrees function and see what we get. All right, probably helps if I spell degrees correctly. So we got that node 0 has degree 4, and that all of the other nodes have degree 0. Does it look like this means anything? If you notice that this is returning the out degree, good job. But do you know why that is? Let's take a look at the adjacency list representation. The adjacency list representation for a directed graph tells us which nodes are adjacent to a given node, meaning there is an edge starting at this node and ending at any of these. So by definition, a node only ends up in this list if it's on an edge that points away from this node. And that's precisely what we need to look at when we're talking about out degree. Let's quit the REPL, go back to graph.py, and redefine a few things so we have a little bit more clarity. First of all, I'm going to give the degrees function a leading underscore. That means this function is somewhat private to this module. If someone else is using this module, I don't expect them to use this underscore degrees function. So here's a new degrees function that only works for undirected graphs. First, it checks whether or not the graph is directed. If it is, it raises a value error and tells us that we cannot call degrees on a directed graph. If the graph is undirected, then it just returns the dictionary from the underscore degrees function. Since we know that underscore degrees returns the out degrees for a directed graph, let's write a function called out degrees that only works for directed graphs. Here's the out degrees function. The first thing it does is check whether or not the graph is directed. If it is, then it returns the dictionary returned by the underscore degrees function. If the graph is undirected, it raises a value error and tells us that we can't call degrees on an undirected graph. And whoops, that should be out degrees. There we go, much better. So to complete the graph.py file, we still need to write an in-degrees function and a total degrees function. And that's going to be your homework. Give it a shot, and let me know down in the comments section what you think a good implementation of that is. In a few days, I'll post another video going over my solution, and we can compare notes. And to make sure that you have access to all the code we've already written in the video, I'll put a link to the GitHub repository where I keep all this code down in the video's description.
Alright, so this brings us to the final topic of this video, degree sequences. They're a pretty neat thing to think about. At least, I think so. So if you give me a graph, and for now, let's just focus on undirected graphs, I can list out all of the degrees of the vertices. So if I have a graph with degree 3, 2 vertices of degree 2, and a vertex of degree 1, I could write out the degrees 1, 2, 2, and 3. And I can do this in different orders. I could start with the largest degree and go down to the smallest one, or vice versa, or put them in some kind of random order. All of these would be considered degree sequences of the graph. Let's take a look at a more concrete example.
So as I said before, the degree sequence of a graph is a list of all the degrees in the graph. Let's write down a degree sequence for this graph. I'll start by writing next to each node the degree of the node in red. So I can write down the degree sequence by listing out all of these different degrees. I could start with, for example, 3, followed by another 3, and then 4 ones. I'll put that whole thing in parentheses to indicate that it's a sequence. Now that's not the only way I could write the degree sequence of the graph. I could order the elements in some other way. Maybe I write it in reverse order, starting with the 4 ones. Or maybe I put the 2 3s in the middle of the sequence. Now these are all different sequences because they're in different orders, but they all represent the degree sequence of this graph. In general though, we'll write the degree sequence in non-increasing order. So we'll start with the maximum degree and end with the minimum degree. One thing that's important to keep in mind about degree sequences though is that they don't uniquely describe a graph. For example, 2 different graphs can have the same degree sequence. So here are 2 graphs. Let's write the degrees of each node next to them in red. Each graph has 2 nodes of degree 3, 2 nodes of degree 2, and 2 nodes of degree 1. So both of these graphs have this degree sequence. But these aren't the same graph. One way you can see that is that this graph has a triangle in it, while this one does not. Or you could observe that in this graph you have a degree 3 node adjacent to 2 degree 2 nodes, but in this graph, both degree 3 nodes have a neighbor of degree 1. So graphs have a unique degree sequence if you ignore how the degrees are ordered, but not every degree sequence is associated to a unique graph. One question you could ask is, does every sequence have a graph associated to it? So if I give you any sequence of integers, could you find a graph for which that sequence is the degree sequence? Well, if you think about it, you can pretty quickly answer no. For example, if I give you a sequence that contains negative numbers, that couldn't be a degree sequence, because nodes can't have a negative degree. But what if I gave you a sequence of all non-negative integers? Say something like this. Is this a degree sequence? Well, let's try to draw a graph that has that degree sequence. There are 5 elements in the sequence, so we know that if there is a graph with this degree sequence, it's going to have 5 nodes. And one of those nodes has to have degree 0, which means it can't be connected to any of the other nodes. Let's say this one has degree 0. We'll draw a dotted line here to remind ourselves that we can't connect that to anything else. The maximum degree in the sequence is 4, so we have to have one node that's connected to 4 other nodes. But we can't do that because there are only 4 nodes here that could have a positive degree. If I try to connect one of them to 4 other ones, say this one, then after I connect to 3, I don't have anywhere else to put my 4th edge. So the answer to this question is no. Which means that not every sequence of non-negative integers is a degree sequence. Now you might say, what if I exclude 0 from my sequence and I look only at positive integers? Well, the answer is still no. I'll let you come up with an example on your own. Actually, that'd be good practice. So that leads us to a definition. A sequence, which I'll call D, is called graphic if you can draw a graph whose degree sequence is that sequence D. So that leads us to another question. Can you tell if a sequence is graphic? Let's look at another example. Here's a degree sequence with 5 threes. Is this a graphic sequence? Now you could just try to draw a graph, and for sequences with just a few elements, that might be a good way to do it. But imagine we had a really long sequence. It'd be really hard to try to just draw a graph. And even if you couldn't draw a graph with that degree sequence, how would you know that you just haven't been clever enough to find the right graph? Well, there's one technique you can use that can help you decide whether or not a sequence is graphic. And you've already seen it. Remember how Euler discovered that the sum of all the degrees of landmasses in his landmass bridge drawings were always equal to twice the number of bridges? In other words, they were always equal to an even number? Well, translating that to the terminology of graph theory, that says that the sum of all the degrees of a graph is even. Nowadays, mathematicians refer to this as the handshaking lemma. The word lemma just means like a useful tool. It's not deemed important enough to be called a theorem, but it's used a lot, so we call it a lemma. And the name handshaking comes from a different interpretation of this problem. If you put a bunch of people together in a room and ask them to all shake each other's hands, then you ask each person how many hands they shook, and add all those numbers together, you'll get an even number of handshakes. That's because you've counted each handshake exactly twice. So let's look at the sum of the numbers in this sequence. There are 5 threes. So if I add all those together, it's the same as multiplying 3 times 5, which gives 15. And this is not an even number. So if there was a graph whose degree sequence was this sequence of 5 threes, then its sum of degrees would be an odd number, which breaks the handshaking lemma. In other words, no, this is not a graphic sequence. But this is not enough information to help us determine whether or not any sequence is graphic. In fact, as an exercise, could you find a sequence whose sum is even but isn't a graphic sequence? See what you can come up with, and let me know in the comment section below. When I post my follow-up video, I'll show you my solution to this question. So now you might be wondering, if I can't use the handshaking lemma to tell me whether or not any sequence is graphic, is there any way to do so?
Well, it turns out the answer is yes, and there's a couple of different ways to do it. That's going to be the topic of the next video. So now's a great time to subscribe and hit the bell icon so you get notified whenever the next video comes out. Thank you so much for watching. I'm David Amos, and I will see you in the next video.